Assalamualaikum and hello everyone. So my name is Ijlal Joy bin Hassanuddin and my ID number is EP01077727. So this is a midterm project for my course which is EEB 1034 which is Digital Logic Design. So proceed to the question. So the question is a home security system is designed so that it sends four inputs. So for input which is A, B, C and D. So for the A is the secret control switch. Line B is the motion detector attached to Windows, and line C is a battery power clock, and the last one which is D is connected to a magnetic sensor to detect open doors. So the following connection produce a logic 1 on each line. So for the control switch is off, and for the motion detector attached to Windows is no movement, and for the clock is between 12 am to 6 am. The last one is which is door is closed. So this is the table for the information given in the question. So we can see that for the input A, which is secret control switch, when it off, input is 1. So when it's on is 0. So for the input B, motion detector Windows, no movement, which is input 1, and if there's movement it will be 0. So for the C, input C, the battery power clock, so it will be 1 if the clock is between 12 am to 6 am, and 0 yes for others than for 12 am to 6 am. For the last one, which is D, the magnetic sensor door, so when the door is closed the input will be 1, and when it open the input will be 0. So we proceed to the truth table. So the question already give the condition when the alarm will be on, which is output equal to 1. So the first condition, we can see that the control switch is off, and the second one is have movement. So we can see that control switch which is A, and when off it means that A equal to 1. So for the have movement is refer to the motion detector which is B. So have movement means that the input will be 0. So A1, our A equal to 1 and B equal to 0. So from the table we need to find which one is A equal to 1 and B equal to 0. So from this table, we can see that the blue one is refer for the first condition. So we can see that the first one is A equal to 1 and B equal to 0. So this will be cause the output 1. So we can see that here is 1 1 1 1 because the input is A equal to 1 and B equal to 0. So the second condition is after midnight, and the second one is door open. So it means that after midnight refer to the clock which is C, and midnight means the input is 1. And then for the door which is input D, the door is open, so when open the D will be 0. So the condition is C equal to 1 and D equal to 0. So this is referring for the yellow color. So we need to find which one is the C equal to 1 and D equal to 0. So for referring to the truth table, we can see that this one is the yellow color. We can see that the C is 1 and D equal to 0. So automatically the output will be 1. So here we have four four output for this condition. Which one for this one, and this one. So the last condition for the control switch, the control is switched on and the door is open. So the control switch which is input A is on, so when it's on is equal to 0. So A equal to 0. So the next one is door open. So door equal refer to the door which is D. So D is open. When open, D is 0. So A 0, D 0. So from the truth table we need to find which one is the A 0 and D 0. So it's refer to the purple one. So the first one we can see A 0, D 0, and the output will be 1. And the second one is this part, A 0, D 0, and the output is 1. So the last one is this one. A0 and D0. So this one is 1. So we finally get the truth table for this alarm. So for the others will be 0. So the green one is referred to the output 1, and for the blue one is referred to the output 0. So the next one is timing diagram or waveform. So for timing diagram, we need to know the truth table. So this is truth table from the previous slide. So for the first diagram, this we can see that is input A. So for this timing diagram, when it step down, it's referred to 0, like this one. But if it's 1, so it's referred to the step up. So like this one, step up, step up. So for the input A, we can see this 0, 0, 0 at times 1, 2, 3, 4, 5, 6, 7, 8, and the others is 1. So step down for the input A, step down, and finally it will be step up at times. So for the input B, you can see that there are 4 step down, 4 step ups, 4 step down, and 4 step up. So from this diagram, you can see that 4 will be step down, and 4 will be step up, and next step down 4, and next is step up 4. Okay, you can see that. So the next one is input C. So for input C, we can see that 2 will be step down, 2 will be step up. It will keep repeated. So this is for the step for the input C. So it's 2 step down, 2 step up, repeated until this one. So the final for the last input, which is D, we can see that there will be the 0, 1, 0, 1, 0, 1. So bersilang. So you step down and step up. So we can see this one for the input D. Up, down, down, up, down, up, down, up, down, up. And the last one is the output. So this output, we can see that 1, 0, 1, 0, 1, 0, 1, 0, and 1, 1, 1, 1. So we can see this one is the output for the truth table. So 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and 1, 1, 1, 1. Start here. So next, we will find for the next question want us to find the SOP form, which is a term. So we need to know that for the SOP form, we only focus on for the output 1. So the first one is the 0 term. Next one is second, fourth, 6, 8, 9, 10, 11, and 14. So this is the for the SOP form term. So we can solve for the SOP form will be V plus. So M0 plus M2 plus M4 plus M6 plus M8 plus M9 M10 M11 and M14. So for the mean term, so we need to see for the first one for the M0. So for the SOP form, we need to know that for the input 0, it will be bar. So for the M0, we can see that A, B, C, D is all 0. So all input will be bar like this one. So the second one is M2. So M2, we can see that 0, 0, 1, 0. So only C is 1. So only C will be not bar like this one. So the second one plus with M4. So M4 here, we can see that only B is 1. So only B will be not bar. Others is bar because it is 0. So plus with M6, we can see M6 is 0, 1, 1, 0. So we can see that A and D is 0. So only A and D will be bar. Next plus with M8. M8, so we can see that only A is 1, so only A will be not bar like this one. and plus with M9. M9 is 1001. So only B and C is 0. So only B and C is bulk, like this one. And plus with M10. So M10 is 1010. So we can see that here B and D is 0. So only B and D will be bulk. Next, plus with M11. So then M11 we can see that only B is 0. So that's why only B here will be bulk. And lastly, plus with M14. So you can see this M14. So M14 only D is 0. So that's why here only D will be bulk. So for our SOP form, you can see that this is the equation for the SOP form. So we use the m in small m because it's a millimeter, which is SOP form. So here is the term for the from the truth tables, which is 0, 2, 4, 6, and 9, 10, 11, 14, which is for the output 1. So next one is POS form, which is next form. So we need to know that POS form, we need to focus just on output 0. So we can see that the first one is this one, M1, M3, M5, M7, M12, M13, and the last one is M15. So we need to know that for the POS form, it will be times with each term. So M1 times M3 times M5 times 7 times M12 times 13, and the last one times with M15. So we need to know that for the POS form, if the input is 1, it will be bulk. It's not same like POS. For POS, the 0 will be bulk. But for the SOP, the 0 will be bulk. But for the POS form, the input 1 will be bulk. So the first one we see for the first term. So M1, here is M1. So 0, 0, 0, 1. So only D is 1. So that's why only D will be bulk. So the next one is the next one is M3. So we can see the M3 here, 0, 0, 1, 1. So CD is 1. So only C and D will be bulk. So the next one is M5. You can see there 0, 1, 0, 1. So B and D is 1. So that's why only B and D here is B bulk. So the next one is M7. So M7 we can see that BCD 0, 1, 1, 1. So 1, 1, 1 is BCD. So BCD, only BCD will be bulk. This is 1. So the next one is times with M13. So M13 is M12, which is 1, 1, 0, 0. So A, B is 1. So only A and B will be bulk. And times with M13. So here is M13, 1, 1, 0, 1. So we can see that only C is not, and C is 0. So only C will be not bulk here, like this one. And the last one times with M15. So M15 1, 1, 1, 1. So all is 1, which means that all input will be bulk. So plus we need to know that for the previous form, the equation is A plus B plus C plus D times with the next term, like this one. It's not same like SOP. So for the PS form, which is this one. So this one is the symbol for the PS form, and we use M, capital M, big M, because it refers to the next term of PS form. So it's 1, 3, 5, 7, 12, 13, and 15. So the next one is for Boolean expression to simplify the equation. So we can draw the logic gates with minimum numbers of logic gates. So first, I use the equation from the SOP form because it's easy to be simplified by using the Boolean algebra rules. So the first step from the SOP form, equation for the SOP form. So first one, what we can do is we can factorize for this one. So first this one is this one. So we can see that a bar b bar c bar d bar plus a bar b bar c and d bar. So we can see that a b d bar is same with this one. So we can factorize. So we will get the c bar plus c, because this one is c bar and this one is c. The next one is same situation. You can see that this one is a bar b c bar and d bar plus a bar b c d bar. So we can see that only c is not same. This one is c bar and this one is c. So we can factorize others. So this one in the bracket is c from this one and plus c bar from this. So next one is this one a b bar c bar and d bar plus a b bar c bar d. So for this one, for both, we can see that a b bar and d and c bar is same, so we can factorize. So we can factorize for the abc, and then left with d bar plus d. So d bar plus d, so it's not the same. And then the last one is this one, a b bar c d bar plus a b c b bar c d. So we can see that only a b bar and c is same, so we can factorize this one, a b bar and c, and in the bracket is d bar plus d, like this one. So the left behind with a b c and d bar, because there's no more equation that can be factorized together. So from this one, we know that this is from the Boolean algebra rules, which is if any input with a bar plus a, it will be equal to 1. So anything that b bar plus b will be will be equal to 1. So from this situation is same. So c bar plus c, so will be equal to 1. So for this one also same goes like this one, so equal to 1. This one also same, this one also same. So we can get this one, as this one is 1. So when a bar b bar d bar times with 1, so we will be still the same, like this one. So just copy back a bar b bar from this one, and this one, and this one, this one, and this one, and then next is a b c d bar. So next we still can factorize, because for this one, both equation, both, we can see that a bar b bar d bar plus a bar b and d bar. So we can see that the a bar and d bar is the same, so we can factorize. So in the bracket will be b bar plus b, like this one. And then for this one, same situation like before, a bar a plus b a times b bar c bar plus a b bar c. So we can see that a and b bar is the same, so we can factorize. So when we factorize, we can see that in the bracket c bar plus c and plus this one, because there are no more equation that can be factorized. So as we know, this one is one of the example above, same situation. So this one will be 1, this one also be 1. So once when is times with the a bar and d bar, so it will be the same like this one, a bar d bar, and this one also the same, a bar and plus a b c d bar. Next, what we can do is we can factorize a, because we can see here is a b bar plus a b c d bar, right? So we can see a here and a here is same, so we can factorize a here. So when we factorize a on the outside, we factorize a in the bracket b bar plus b c d bar. So for this one, this is one of the Boolean algebra rules. So from this, if the A input A bar plus if we solve for the this one, which is A times B, will be equal to A bar plus B. It means that the A here will be eliminated. So for example, I just a question. For example, this one is A plus A bar times B. So the A here will be eliminated. So which means the final will be A plus B. So for this situation, we can see here is B bar plus with B. So the B, this B at the right side is not bar. So this side, the B at this side, the right side will be eliminated. Following the Boolean algebra rules. So the result will be A bar D bar plus A B bar plus C D bar. So the B here will be eliminated because this one is B bar. So this one is not B bar. So this side will be eliminated, not this side, the right side with the group or others input. So next we expand back. So we expand back for the bracket. We will expand back. So we will be get the A bar D bar plus A B bar plus A C D bar. So next we can factorize for the D bar, because for this one A bar D bar and A C D bar. So we can see that D here and D here is the same, which is D bar. So that's why we can factorize like this one. So if we factorize D bar, we factorize D bar, and here is A bar plus AC. So like the situation before, like this one, we can see the A bar plus AC. This one is A, this one is A, but this one is bar. So we can see that A here with A with no bar is at the right side with the others input. So this A with no bar will be eliminated, and A bar here still stay here, and C also stay here, following the Boolean algebra rules. So the result will be A B bar plus D bar in the bracket A bar plus C. So A here is eliminated for because it follow the one of the Boolean algebra rules. So here is our simplest Boolean expression, the simplest equation that we get. So this equation we will use to do the logic gate diagram. So we move the logic diagram. So we get the simplified equation, which is this one, like before previous slide. A B bar plus D bar in a bracket A bar plus C. So if you can see here switch at the left, so the first switch is A, input A. So the second one is switch B, which is input B, and this one is C, input C, and this one is D, input D. So for the first one, we can see here is A B bar. So how we want to draw it? So first we need to know this one is times, right? A times with B bar. So we need to put the times. So when times, it refer to the n gate. So n gate is like this one, curve, and then back is straight. So for this n gate is A and B bar. So for the first input here is connected to the A, and the other one will be B bar. This one is B right. So if we want to be input B bar, we need to put the NOT gate here. So that's why we put the NOT gate here and connected to the NOT gate. So that's why this because this will be the result of B bar. So we settle with the first part here, and then the second part here is here A bar plus C. So we can see that the here is plus, right? So plus is refer to the OR gate. So for the OR gate, the difference with AND gate is at the back we can see that the it's not straight, a little bit curved, and the in front is more sharp here. It's different with the AND gate. So we can see that the for the OR gate is A, A, A bar and C. So the first input here, first leg here, is from the A naught. So A naught is here. So why this there is a NOT gate here? Because in the equation is A bar. So that's why we need to put the NOT gate here. So it will be the A bar, which is A naught. So connected to here, and the other one is C. So C is from this one. So that's why this one, this the others input or leg is connected to the C. You can see the next we need to see the end this one, which is D at outside. So actually for this one we can see that we already get the A plus C, right? So new we already settle it. So next one is this one with D. So this one D times with bracket A bar plus C. So times here refer to the AND gate. So this is the shape for the AND gate. So for AND gate, there are two legs to input. So for the first one is D bar. You can see here this bar. So this why this input, this leg for the AND gate will be connected to the D. Why this one is not gate? Because the equation is D bar. So that's why this one there is D not gate. So D will be bar, which is not D. It's connected to this side, and the other one is connected to the in the bracket A bar plus C. So from this one, so this one just connected to this one because times because this end is times D bar times with this bracket. So this bracket from this logic. So it's like this. And then the last one is this one. The last one, function. So we can see here there are two brackets, which is the bracket for the first bracket is A plus B bar plus, here is plus, and the other bracket is D bar, and the bracket like this one. So we have two bracket here. So it means that plus here in the middle plus. So you refer to the OR gate. So OR gate is like this one. So there are must be two input because it's two input here. So the first input is A plus B bar. So this one is connected for this one because it's already formed. So this is the logic the gate for the A plus B bar. So just connected to here, and the other one, the other bracket is this one is from this one. Like we already made it just now. So just connected to this leg, and then last one to the output. So this one is the bulb is output, which means the alarm is the alarm. So this is the logic diagram for this alarm. So the next one is universal gate. So the question, the project asks us to convert the original circuit, the alarm circuit, by using only using universal gate. So before we convert, I will explain what is universal gate. So a universal gate is a gate which can implement any Boolean function which is gate without need to use any other gate type. So it means that universal gate is gate that can produce another gate. For example, this gate can produce AND gate, this gate can produce OR gate and NOT gate by using universal gate only. So the example of universal gate which is NAND and NOR gate. So this is only the universal gate, which are NAND and NOR gate. So it means that this NAND and NOR gate can produce any gate that exists. So the first one, before I begin my explanation, I will only explain about NAND gate. So how we want to produce AND gate by using NAND gate? So first one is AND gate. So this is the original gate AND gate, two input A, B, Y. So how we want to produce AND gate by using AND gate? So this is the shape. So to produce AND gate, we only use two NAND gate. So here we can see two NAND gate here, but the one gate here have two input, but the other one only use one input. So it means that this first AND gate will connected directly to the this AND gate, and another one AND gate. So this have two input, this one have one input. So I will compare with the result of AND gate. So this is the original AND gate truth table, and this one is the NAND gate truth table. So we can see here, this one is AB here. So AB is the input. So this one also AB here, the original gate. So we can see that there is a same input, which is 0 0 0 1 1 0 1 1. So this also the same 0 0 0 1 1 0 and 1 0 and 1. So this is the result, and this is the result. So we can see that it is the same. So it means that this NAND gate can produce AND gate. So this is the arrangement of the NAND gate. So the second one is OR gate. So this is the original gate for two input, which is A, B, and one output, which is Y. So this is how the NAND gate looks like for OR gate. So we can see here it will use three NAND gate, but two NAND gate will use one input only, which is A, one input, and this one only one input only, which is B. So this both NAND gate will connected with the another NAND gate. So the three NAND gate here. So we compare. So this is the original OR gate truth table. So this is input AB, also same AB. So 0 0 0 1 1 0 1 1. So also the same here, 0 0 0 1 1 0 1 1. So X here is the output, and Y is the output for the original OR gate. Yes, OR gate. So we can see here 0 1 1 1 0 1 1. So same result. So it means that this NAND gate, this arrangement can produce OR gate. In the last one, I will explain is NOT gate. So this one is the original NOT gate. So NOT gate only one input, and this one is the output B. So for NOT gate, we only use NAND gate, but we must make sure that the NAND gate, the NOT gate, the NAND gate here only one input, which is AB. So AB must the same input. So I will compare the result. So this one is the original NOT truth table. So this one A here, A, the original gate, A here, and the other AB. So AB is same lah, AB. So 0 0 0 1. So this one also 0 1. So the output for the NAND gate here is X. So X, and the output for the original NOT gate is B. So B. So the result 1 0 here and 1 0 here. So it's the same. So this NAND gate can produce NOT gate also, but make sure that the input for NAND gate is only one input. So we already know the universal gate, which is NAND gate. They can produce another gate by different arrangement of NAND gate. So we proceed how to convert the alarm circuit just now by using universal gate. So the first diagram here is the original circuit that I already explained to you guys just now from the previous slide. So here is switch here. So switch here is referring to the input. So the first one is A, B, C, and D. So here is the nodes as our guide to convert this circuit. So the first one, we want to convert the not get in the blue and in the purple circle. So here we can see this is the not get, right? So not get here, we need to use the one only NAND get, but the input only one. So two inputs here connected to the one input, the same input. So it means that one input only, same situation. So we already changed for this one, and then the next one is this one, another not get. So also the same situation. We just replace with the NAND gate, but only use one the same input, which is B here. Yes, you can see here B here. So the next one is the green one, which is the OR gate here. OR gate. So OR gate, what we have learned just now, OR gate will use three NAND gate here. So three NAND gate here. So we need to make sure that the two NAND gate here only use one input. So here we will change with NAND gate, three NAND gate, but the back is by using one input. So here two input of this NAND gate will connected the same input. So the same input. So also the same is one. This NAND gate, the two input here is the same, which is C here. And then these two NAND gate will connected to the another NAND gate here. So this one is for the OR gate. So the next one is for the pink circle, is not gate. So same like just now, only replace with the NAND gate, but the input is still the same. Must the both input must be the same. So which is here we can see is D. So both input here is connected in the same, which is D. And then the next one, the purple one. Okay, the purple one here, the blue one. So blue one is AND gate. So also the yellow one and also so the same gate. So how we want to convert to the universal gate, which is NAND gate. So you put this node, we used two NAND gate here, but the second NAND gate only use one input, which is from the first NAND gate. So we just replace. So we can see here the first NAND gate here is two input with two different input. So this from this one, from A, and this from this one, the not B, and then connected to the another NAND gate with one input. So the output for the first NAND gate will connected to the input of the second NAND gate, which is the same input here. Same situation like this one, the yellow circle same. So we can see that both is a NAND gate, AND gate. So use to get to NAND also. So the last one is the OR gate. Same like the green circle here. We will use the three NAND gate here and two NAND gate with one input here, same input here too. And the both NAND gate will connect another NAND gate and done. So this is our converting our universal gate, our circuit by using universal gate only. So the next one is the next condition. So the information is anytime we have an even number of inversion in the form of not function which are non-gain, we can replace them with a simple piece of wire or single wire. So it means that if there are two or four not gain, it can be replaced by single wire. But this in this case, we only discuss with the NAND gate. So for the NAND gate, not gain by using NAND gate is by using one NAND gate only, but the input is one. So for example, like the example shown in diagram in the slide. So here have two NOT gate, but in the universal gate form, which is NAND gate. So here we can see that there are two and both have one input because it means the NOT gate. So why this situation can be replaced with a single wire. So this one is 2 gate, which is even number, so it must even number like 2 4. So for example, this one is A, so the input is A, and the result for the first NAND gate is B, and gate is B, and the output is C. So for example, for the A, when the input is 0, it will produce B, which is 1. So then the input go to the next AND gate, and they will produce 0. So we can see that the output will get back the original input like before, like this one is 0, so the input also 0. So the system uh, get back the result from the input. So for example, second example here is A1, so A1 here, so go the AND gate, so because 1 1 result AND gate will be result 0, and then 0 to the next AND gate, NAND gate, you will get 1 back. So it means that there are no change actually. We can compare for the input and the output. So there is no change. So that's why this truth table show that why this situation can be replaced with a single wire. So based on this circuit that we have made just now from the previous slide, so for the first one is here situation like this one. Why this one can be replaced with a single wire? Because this one we can see that there are two not gate but in the form of NAND gate. So for the first NAND gate here is two input, right? But the two input actually from the one input, the same input. So same like the second input, the second NAND gate here also the same. The input is also 1. So that's why is same like this condition. So the next one is this one, because there are two NAND gate here or not gate. So for the first NAND gate here is one the same input also, and this one also the second NAND gate also have the same input, one input here. And then the last one is this one. So we can see the first NAND gate here has one input also, and the second NAND gate also one input also, the same input. So why this one? Why this one? My mouse here is it's not the same like this equation, because for this NAND gate, yes, it has even number of NAND gate, but it's not actually it's not function. It's not get actually, because this NAND have two input actually. So this two input is from the different input actually. It's not one input. So also this one, the second NAND also have two different input. That's why this one is not same situation like this one in the black circuit. So based on this situation, we already find that have the same situation. So we can replace this one with a single wire. So this one eliminated, and the input A will directly connected to this one, and this one eliminated, and this NAND gate will directly connected to this one, and this one eliminated, and that's why this NAND gate directly connected to this NAND gate. So this is our final circuit for this alarm by using universal gates. So the last question the project asks us to do is to simulate the result of the circuit. So this is the circuit that we convert just now, the alarm circuit they use on that only use NAND universal gate, which is NAND gate. So for this simulation, so when this one is the first input A, this one second B, C, D. So for the input 0 is referring to this switch in the white color. So we can see the white color here. So if the white color, it means that the input is 0. So here is the 0 white color. So if the color of this switch is blue like this one, so it means that the input is 1. So for the bulb, so for example the bulb is here is blue, so it means that the blue means the output is 1. So for the bulb is not light on like this one, it means that the output is 0. So we can see here the 0 0 0, the input here is 1. So we can see here all the input A, B, C, D is 0 0 0. So the input is 1. So the first condition is correct. So the second one is 0 0 0 1, which means A0, B0, C0 and D1 here. So the input here, the bulb is not light on, so it shows off. So it means that the input is 0. So the result is the same like in the truth table. So next we move to the second one. The third one is 0 0 1 0 0 0 1 0. So the result here is 1 because the bulb is light on. So the result is the same like the truth table, which is 1. So we move the next one is 0 0 0 0 1 1. So 0 0 1 1. So the 0011 will produce the output 0. So we referring to the truth table, 0011 is 0. So this condition is also correct. So move to the next condition, which is 0 1 0 0. So we can see here is 1. So refer to the truth table, 0 1 0 0 is 1 also. So move to the next one, which is 0 1 0 1 0 1 0 1. So wait 0 1 0 1. So we can see here it's not light on, so it means that the output is 0. So referring to the truth table, 0 1 0 1, so 0. So the result is still correct. So we proceed to the next one, which is 0 1 1 0 0 1 1 0. So the result is 1 here because the light on 1. So refer to the table, 0 1 1 0 is 1. So correct. So move to the next one, 0 1 1 1. So 0 1 1 1. So the result is 0. So refer to the table, 0 1 1 1 is 0. So correct. So move to the next one, what 0 0 0. So the input is 1. Refer to the table, 1 0 0 0, also 1. Correct. So move to the next one, which is 1 0 0 1. So the input in this simulation, this circuit, is 1. So refer to the truth table. Our truth table just now, 1 0 0 1, also 1. Correct. So move to the next one, 1 0 1 0. So result is also 1. So refer to the truth table, 1 0 1 0, also 1. So the circuit still correct. So move to the next one, which is 1 0 1 1. So the result is 1. Refer to this our truth table, 1 0 1 1. So the result is also 1. So the circuit still correct. Move to the next condition, which is 1 1 0 0. So 1 1 0 0. So the output is 0. So refer to the truth table, 1 1 0 0. So 0. Correct. Move to the next one, 1 1 0 1. So 1 1 refer to the truth table, 1 1 0 1. So the output is 0. So it is just the same. So the second last is 1 1 1 0. So the input here is 1. And refer to the truth table, 1 1 1 0 is 1. So correct. And the last one is 1 1 1 and 1. So the result is 0. So refer to our truth table, 1 1 1. The output is 0. So it means that our circuit is is correct, 100%, 100% correct. Based on our simulation just now, all the result by using the input following the truth table, the result is the same. So it means that this gate is correct, even though this gate only use the universal gate, which is NAND gate. So that's all from me. Thank you so much.